so let us continue today the reminder of the design against blast loading. I think yesterday we were looking at the requirement, basically how you evaluate and what are the design criteria. And if you look at it, basically the acceptance criteria is based on the serviceability requirements and the strength requirements. And the strength requirements, as usual, if you are looking at allowable stress design or the other forms of design where you use the plastic capacity, but most of the time for blast loading we still use the allowable stress method. Only when very rare cases we go into basically plastic design methods, and the deformation limit is something that we need to limit it indirectly. So basically the deformation limit is depending on the location of the equipments and the facilities, and also the disconnection of the structure with the main structure. Basically what you do not want the large displacement to make the plastic hinge formation at the two ends. For example, if you take a simply supported beam, you allow the beam to bend substantially larger deformation, then the ends will form a plastic hinge by which it will just fracture. So basically no part of the structure should impinge on the critical operations on the equipment on the other side, and the deformation should not collapse or make the structure to collapse because the hinge formation, either 2 numbers or 3 numbers depending on the bending moment. So basically the idea behind why we do not want the structure to collapse, because we need to give sufficient time for the people to run away to a place which is safe enough for them to be evacuated. That is, sometimes we call it temporary safe refuge, is just a technical notation given in the codes and guidance. TSR is nothing but some place is designated to be a safe place for them to stay there for a slightly longer time, waiting time, so that basically either they can get evacuated by helicopter or boat or other means. So every platform normally will have a temporary safe refuge at a particular designated location. You are supposed to assemble in case of an emergency like fire or other forms of accidents. And along the route, basically when they are running around towards that particular location, the escape path must be designed in such a way that the collapse does not happen. The idea is, so you have to identify the elements which are required to be satisfying this condition and design those elements accordingly. So if you look at the design load, I think yesterday also we were looking at the pulse loading. The duration of pulse is basically tau, and the natural period of the structure that you are looking at. For example, when you are looking at a escape path, you have several beams supporting the escape path, and each beam should be looked at as an individual element. It is a local design, it is not a global design we are looking at, and basically the natural period is local to that particular beam, not like the complete structure. And the design method, or so called the analysis method, depends on the behavior of the structure, whether it is dynamic or static or even highly displacement based structure. Basically if you look at the loading ratio, the duration versus the period of the structure is very small, then you may have to use the energy method, which normally we use it for some class of problem like dropped objects. We look at the impact energy and the energy absorbed by the structure. As long as the load is very short duration, short pulse, and just have an impact, and typically we calculate the impact energy by means of the weight times the height, mgh you can calculate, and the energy absorbed by the system can be easily calculated by the work done. So as long as the energy absorbed by the structure is larger, the system is not going to fail by basically brittle nature. So that is one of the method which is conventionally used for most of the the impact type of problems. And if the loading is between 0.4 to 2, that means the duration to the period of the structure is slightly longer duration, you could actually use a dynamic analysis method where you look at the response of the structure using a simplified either single degree of freedom system or multiple degree of freedom system. I do not know whether you have taken classes in dynamics. Basically single degree of freedom is this motion in one direction. For example, each particle in a structure can have a 6 degree of freedom, basically 3 translation, 3 rotations. In this particular case, what is our interest is the lateral motion of the structure or the displacement of the structure. Typically if you take a wall, the horizontal displacement is what we are very much worried about. Basically you do not want to have the structure go and hit or impact against any other equipment and dislocate. So, basically that's so most of the time we try to use a single degree of freedom system. If it is only just a simple wall or a beam, you do not look at anything else other than just the lateral displacement, and many times it is very simple, quite easy to do a hand calculation. If it becomes a multi degree of freedom, of course, then you may use a assistance from computer software, and then when the loading is substantially longer duration, then you can go for a simple static energy method, which is equal to a stiffness method. Basically a simple analysis can be performed. Deformation limit, in many cases we directly or indirectly we have several ideas of limiting without doing design. For example, I think most of you are civil engineers, you might have studied in concrete design. We try to limit the span to depth ratio, for making sure that the deformation is within limits. You do not even need to do calculations. For example, simply supported span to depth ratio is limited to say 20, cantilever 10, 12, something guidance which if you follow, most probably you will not have a problem with the deflection. In this particular case, basically a typical value is span by 40, because of the impact loading. So, it is just almost a factor of safety of 2. So, basically the proportion by span, the larger the span, then you will have a larger amount allowable. Absolute deformation is something that we need to also set because of the spacing between the structure or the wall to the equipment in the vicinity, typically about a meter. In practice normally we give a meter space, because if it is less than a meter space, for example, you do not have access to the equipment on the other side. So, normally we give about 1 meter, 1.2 meter. So, once you fix up this, the absolute deformation, then probably working out or back calculating the strain limits is easier, because you take a beam, you allow 1 meter to deflect, then automatically you can calculate back what could be the potential strain induced on the beam at the ends or elsewhere. So, that basically the strain limits is indirectly coming from the deformation limits. Now, how much strain any system can take depends on the type of material. For example, you take a glass, you take a rubber and a steel material. You can easily see that the glass will not even take a fraction of a percentage. So, it will just break because the material is brittle in nature compared to steel, and the same thing goes to rubber. It is quite elastic, it can take a large amount of strain, as much as 20-30%, whereas steel can take, especially the ductile steel can take 17% at low strain rates, not very fast, slow increase. So, you can see here the ductility ratio is defined in terms of elastic versus elastoplastic, basically to see that after elastic deformation how much strain the system can take, so that the failure is not immediate, it can actually go for a slow and ductile failure. So, the ductility ratio is one of the area where lot of research has been done. In fact, we have already got some idea about elastic modulus versus plastic modulus. I think in a few classes back we were looking at for different sections, different boundary conditions. So, one of the thing is the ductility ratio is not only affected by the material selected, also affected by the geometry and also the boundary conditions and the type of loading. I think all of them we have had a look at earlier on, we just have to re-look at it in terms of ductility ratio. Basically, the steel sections can sustain plastic deformation provided they do not have other forms of failure. For example, you take an I section versus a tubular section, the predominant difference is buckling. I sections have a torsional buckling, whereas the tubular sections have a local buckling because of the d by t ratio. So, as long as both of them does not happen, both of them will reach the maximum plastic capacity, but again depends on the span. So, basically we need to look at the span, the section property and type of loading and the boundary conditions. All of them put together, though you have a very good ductile steel and calculate back what is the ductility ratio, the ratio of deformation at elastic to the plastic, that the maximum deformation the beam can take, because we are looking at mostly the beam type of element for design in offshore structures. One of the limitation, basically though the beam can take, many times that is what happen, for example, you design a residential building, you have architectural finishes, the structure actually can take slightly higher or increased deformation deflections. But why we want to limit to lower value? You do not want to see a crack appearing on a structure which prohibit the users to be little bit scary. Basically they do not want to go there because you can see this cracks visible. So the structural deformation actually will reflect on the architectural finishes. For us, I think offshore structures we are not worried too much, but what is our worry is the fire protection coating what is applied onto the structural elements will start cracking. Once you have a crack, the effectiveness will be gone because the temperature will be directly attacking to the steel structure. So that is one of the worry where you may limit the strain to a limited value rather than going to the maximum strain value. A typical strain limits given by some of the codes which I have just tried to summarize. Basically tension member you can go for 5% instead of 17%, though we say we can go for 17% up to, and basically the other members in compression and bending, I have just taken one typical example from BS or EC codes. You can go for 5%, 3% and other open sections to 1%, compared to we allow 0.2% for elastic or allowable based design, which all our linear stress strain diagram is at 0.2% strain. So you could see here from 0.2% we are trying to go to 1%, 2% and 5%. So you use the same equations, allowable stress equations, and calculate back what could be the possible deformation or deflection of a beam. If I use 5% strain limit, you will see that it will be very large, but when the deflection is large, by that means itself all your theory is not correct, because the first assumption we make in the elastic beam bending theory is the deflection is small. So the deflected configuration is same as the original beam. That is the first assumption you make, and that will be violated. So that is why whenever you are going for this large strain problem, you have to look for the updated Lagrangian. So basically every time you apply a load, you divide the load into several sub steps. Each time you apply a load, find out the deflected configuration, recalculate the stiffness based on the deflected system, and then apply the additional load and just keep on going. So basically that is where the idea have to work out. So most of the large strain problem we have to go for a nonlinear analysis, geometric nonlinear analysis. The other one, basically the important problem is the shrinkage of the beam. You take a simple beam, rectangular in cross section, you apply a central point load. When the beam bends, what happens? The bottom surface experiences tension, the top surface experiences compression. As long as the deflection of the beam center is smaller, these extension and reduction in the length of the beam surfaces could be very small, the difference, the compression and the tension. Whereas if the deformation is so large that you will see that the shrinkage at the top is going to be substantially larger and the elongation at the bottom is going to be very big, and that basically have to be worked out. The shrinkage limits, sometimes instead of specifying directly the deflection, you will be given a shrinkage limit of particular material, because I got architectural finishes, I may have other coatings. At that particular shrinkage limit, the material disintegrates. For example, you have a intumescent coating on top of the steel beam. When you bend the beam to 5% strain, you will see that none of the coating exists there, it's all gone. So you will have to get the shrinkage limits from the material manufacturer, that it can take only say 1%. Then you have to calculate back what could be the potential deflection that you can allow for the beam and work backwards. So all this is basically to not just only look at the mechanics side of the problem, also the serviceability and operability of the system in question. So member shrinkage is one thing that we need to work out. So basically the ductility ratio is the total deformation at failure or just close to failure at ultimate load to a deflection at elastic limit, which is at 0.2%, which will give you an idea how much deformation a beam or a plate or a system can take prior to failure. So that gives you the range, as long as if they are equal. For example, ductility ratio is 1, not a good idea, because as soon as it reaches the yield, the beam is going to fail, and that will never be called a ductile failure, it will be called brittle failure, which is what we do not want to happen. And you have to select system, material and loading systems and basically your cross sections such that ductile failure. Always every design of structure, whether it is onshore, offshore, everybody is looking for a ductile failure of the system, not the brittle failure. So, as I mentioned earlier on, it depends on so many factors, the fixity, not only beam, it could be plates also, and you have type of loading and the shape of stress strain curve, whether it is just elastic and perfectly plastic, no good, isn't it, because it is basically bilinear, and once it reaches and large deformation will be immediate, and that is exactly we were talking about, I think several classes back. The difference between yield strength and the ultimate strength, the larger and larger is good. If you have smaller and smaller, there is no redundancy in the stress strain curve, and the rate of loading, basically whether it is quick pulse loading or sustained loading for a longer duration, and the hinge formation, basically the plastic hinge. I think we have got little information about simple beam system to calculate the plastic moment capacity. I think we will just revise again one more time. If you look at the some of the textbooks or code guidance, you will get this derived formulas. We could also derive based on what we have learned on the beam fixity and the stress strain curves. This is a summary of equations that is to give you an idea for ductility ratios or ductility factor, which is just sometimes do not get confused with the symbol mu. In this particular one they have given mu, normally we use mu for Poisson's ratio, so just do not worry about it. Basically for a different beams from cantilever and supported beams on both ends, simply supports, fixed beam with different types of loading, the summary of equations to calculate the ductility ratio always must be greater than definitely 1. If it is 1, that means the system is very weak in carrying any load, basically it will fail once it reaches the yield strength. So, you see here epsilon P is the plastic strain and epsilon y is the basically I think it should be 17%, basically the elastic limit, and 0.17 instead of 0.2 for grade 50 steel for elastic limit, and Sx and Zx is the elastic and plastic modulus, which I think most of the sections we have already derived some time back. I sections, circular sections, I think we have derived both. So, you should be able to substitute this, you can get the value, and you will see that depending on the type of cross section, depending on the ratios, you will get the different values. In fact, the summary of such has been taken from one of the Eurocode for grade 50 steel. You will see that the numbers ranging from as low as 1.6 up to 12.5 is the large number for most of the beams, you can see here, especially the class 1 and class 2. Class 1, class 2 is basically the classification whether it is compact or plastic sections. I think one of the class we will try to go into this classification of open sections, which I think we have not done so far. And also for plates, most of the time we use plates for the fire and blast valves. So, basically you can see depending on the boundary conditions, you can have larger number. You see here the fixed ends for the plates, all 4 edges are fixed, you have a very large ductility ratio. So, this gives you an idea how much redundancy the system has got prior to complete failure. Now, idealization, unfortunately you have not taken the dynamics course yet, or some of you have taken previously, not yet. So, basically the single degree of freedom is nothing but the dynamic response of a beam or a column or a plate system against external loading, and basically single degree of freedom is one particular displacement is modeled for analysis. For example, if you take a beam transversely loaded perpendicular to the axis of the beam, and when we look at the vertical displacement, so it is only single degree of freedom. If you are looking at a horizontal displacement, axial deformation, then it becomes 3 degree of freedom, and as together if you are looking at the rotations, x rotation, y rotation and z rotation, then it becomes 6 degree of freedom. So, basically single degree of freedom is one particular axis of deformation is included in the calculation. Most of our beam calculations, if you look at it, we are only worried about the vertical deformation, basically is a single degree of freedom. It is just a notation in dynamics, So, basically you can model all these systems. For example, you take a beam, 2-dimensional beam, and some boundary conditions are given at ends. You have a transverse load perpendicular to the beam axis at the top flange or bottom flange, and you can model this as a simple vibrating problem perpendicular to the axis. So, most of the textbooks will have formulas to find out the the displacements and the moments, and can be used very easily. In next slide, I have got summarized table for both dynamic and static, and probably right now you may not be able to basically memorize it, because you need to take the course, so that you will be able to use it appropriately. Somewhere here, I have just given only 3. If you look at this particular code book, you will have several more, probably I think 3 or 4 pages, just to give you an idea what really happens. But in fact, we derived some of this formula in one of the classes. I think in the previous class, for point load and the distributed load, we derived the maximum rotational capacity, I think the last time. So, similarly for other forms of loading, this summary is given. The reason why we want to do this is basically we want to find out what is the dynamics of the system plays a role on this. Basically when the load is dynamic, the dynamic response needs to be looked at, the response with respect to varying load. In this particular case, is not a 100% varying load, it is actually a short pulse and stops, compared to a wave load where it is actually varying continuously. So, the response could be slightly different. For that to happen, we need to understand and calculate the natural period of the system, which is a very simple stiffness and mass equation. If you look at this, I think even you might have studied in your basic physics, square root of m by k, simple idea. As long as you know the mass of the system, whether it is a distributed mass or a lumped mass at the top, you can calculate the period, which I have just rewrite in a slightly different form, does not matter. Basically the idea is you need to know the mass of the system and the stiffness. When you are solving a static problem, you do not look at the mass, you just look at the stiffness. That is what the most of the bending moment formulations based on, the inertial effect is negligible. That is what the assumption we make when you try to derive your simple beam bending theory. The acceleration is so small, you can ignore it and basically assume that the inertial force is not contributing to the total displacement of the system. That is what makes you the problem so simple, that you just only solve for stiffness and displacement. So, in here what we are looking at is the contribution of the inertial effect to the total deformation is not ignorable or not too small. Then you find out what is the vibration frequency and what is the loading frequency and compare it, and that is exactly the idea behind. So, if you have a distributed mass and you want to distribute to a particular degree of freedom, for example, you take a beam, the mass is all along the length of the beam, it is not one particular point, then you need to designate to the lumped mass to either at the top or at the bottom. So, you depending on the mass factors, the distribution factors, you can sum it up as a characteristics mass. Sometimes we call it effective mass, and remember most of our offshore problems we need to take into account the added mass, because it is especially the substructure. Superstructure you do not need to really worry, because it is above water. A typical stress strain curve, which for idealization is a bilinear curve. So, basically you see here a single line with a perfectly elastic and plastic. Basically is not a good idea to have it, but for modeling several times we use this, because if you have a nonlinear something like this, then you need to go for a nonlinear analysis. To simplify, many times we make a bilinear stress strain diagram and try to calculate simplified solutions, of course by hand, not by computer program. If you have a computer program to do, then you do not need to assume such type of stress strain curve, you always can go for a nonlinear graph like this. So, the dynamic load factor, I think indirectly if you study dynamics, we call it dynamic amplification factor, but in this particular aspect we call it dynamic load factor. Basically the increased reaction of the system to a applied load. So, how do we find out is basically the ratio of the dynamic response or dynamic reaction to a static reaction. Basically, if you take a simple beam, apply a central point load, you will have half at both ends. When you apply the same W as a impulse, as a short duration impact load, then the increased reaction you could easily find out from the formulas that we can derive, and that gives you the ratio called a dynamic load factor. The reason why we want to find out, we want to solve this complete fire and blast valve design in a simplified manner instead of going for a nonlinear analysis. You do the static response, you find out what is the DLF separately, apply on top of it. So, basically quicker design method, it is a shortcut, but of course serves the purpose for which we want to design the firewall. That is what you will see from the table here, the derived static reactions and the dynamic reactions. So, basically the ratio will give you the DLF, which we could derive, but I think this is part of your dynamics course, which will take considerable amount of time. That is why I am not deriving in this class. The next one is a simple dynamic response. I just wanted to highlight before we summarize basically the response of a simple beam system to a triangular pulse loading. It is just a basically idealized pulse loading like this with symmetric rise time and the fall time, basically just a nice simple loading to be analyzed quickly by hand. So, you could find most of these equations in any dynamics book, starting from your dynamic equation, supply this loading and find out the response. The response contains three parts, especially you see here is between the time of pulse, basically between 0 to 0.5, that means on the rise time and on the fall time, and after the load is over. So, you will see the response will be definitely different compared to if you have this triangular pulse keep on coming back and again, then there will be a sustained response. We call it transient response and the steady state response. When you are doing your calculations, you will do exactly this. If you have a continuously applied load, then the steady state response will start from a few cycles later, but continue for a longer duration because the load is continue to be there. In this particular case, you see here the pulse is applied and that there is no more loading. So, you will have an increased response first and then go for a reduced response afterwards, and then it will die down because there is no more loading coming there. So, basically these three component responses can be computed, and I just graphically shown here, that is what the idea. So, the response is peak typically reaches, is a normalized response. So, basically you see the maximum response within the limits of your the applied load, and then go for a sustained or so called steady state response, then it will die down afterwards as long as there is a damping in the system. Now, I just summarized 4 of the cases, plotted the basically the dynamic response factor, we call it basically the dynamic load factor, in which we just now calculated dynamic reaction versus the static reaction. It is one and the same. So, in here you see here for 4 forms of loading, 0 rise time, smaller rise time, slightly increased rise time, 0.3 here, 0.1 and it is 0.5. You see the ratio of factor as much as 2 here and reduces to 1.5, 1.6 and then 1.5. So, you could see here most of the simple beams you have a increased deformation factor, basically almost 2, as long as you are able to predict this particular response to your class of problems. Then you can multiply whatever the static displacement you are calculating, because we have assumed a bilinear elastic perfectly plastic system. This is only a simplification we are making for our hand calculations. Most of the design practice nowadays is based on this. Of course, this is not mandatory. If you have your time and effort, you can actually go for a nonlinear stress strain analysis, but most of the design practice we make this because it is quicker and serve the purpose. So, that is why we need to derive such dynamic factors. So, load is applied dynamic, we know indirectly the dynamic factor is say x, and you calculate your simple beam static displacement, static bending moment, static stresses, multiply that with these factors. So, that is the idea behind. Many times we do this even for big jackets. So, basically the idea of calculating the dynamic load factor or dynamic factor is to account for the system dynamics and not going into nonlinear analysis. Simple static analysis will cover the response of the system. So, how do we design the firewall is basically several steps, all of them have been discussed. First one is the fire scenario. I think we have already discussed whether it is a pool fire or jet fire and fire ignited blast or blast generated fire, all that have to be described, so that you can find out the extent and the area of the loading. And the overpressure scenario, basically depending on your porosity of the structure and the wall configurations and the ventilation, and establish the response under increased temperature. So, which I think very simple idea. We have the stress strain characteristics under increased temperature for steel, and the reduction factor for yield, reduction factor for modulus of elasticity, and approximate methods also we have discussed. So, you need to establish the applicable yield strength, applicable modulus of elasticity, and keep it in one side. You have established the design pressure, which will come from a specialist study. Most of the time computer softwares are not that good. References from various the prototypes testing or some recommendations from other guides will be used. Many times people use the risk versus the value, because based on history, if you want to take lower risk, you design for a higher blast pressure. So, there are several guidebooks which give you use design 1 bar, 2 bar, but in the recent times quite a number of 3-dimensional modeling software I think are available and could model complete platform and make a ignited blast and can calculate, and the software is able to simulate such overpressure values. But again it depends highly on how the model is done correctly, because the real scenario versus the computer model prediction could be quite approximate. So, this blast overpressure will be recommended for design by the risk assessment group. They will assign you the value that you can use for it. For structural engineers, the most important is the third point, to assess and establish the characteristics of material for yield point and the modulus. Then find out the dynamic amplification, dynamic load factor, which you need to have a basic understanding of system dynamics. If it is a simple beam, I think what we described is okay, but if it is a multi degree of freedom and basically you have a complete frame to be designed, then probably by hand calculation will not be able to do properly. But for classroom exercise, I think most of the problem we are going to solve is either a beam or a simple rectangular plate. So, you can establish DLF and establish deformation limit, I think which we have sufficient information now, 1 meter, half a meter, 500, 600 mm, then you can proceed and establish strength limit, basically whether you want to design by allowable stress method or you want to design for plastic deformation capacity. So, once you do this, I think the procedure is very simple. As normal you do a simple beam design. For example, we decide to do a allowable stress design. You do not need to go anywhere, simply follow the steps what we have done so far. Only two things you need to do: change the material characteristics, increase the loading factor, isn't it? And the allowable stress needs to be increased by X amount. In this case, we will say 50%, 60%. The codes allow as much as to 70%. Like when you design a structure for earthquake, you increase the loads, the stress levels to 70% of the conventional or normal stress levels. So, these are the three things you will. There is no other difference, because of the presence of the temperature, the material characteristics changes. Because of the presence of the blast loading, the load is dynamic. So, you incorporate the dynamic factor, and because of the deformation is large, you may have to consider increased strain, and that increased strain you will go back and calculate and find out what could be the potential reduction in yield and modulus. So, basically that is the simple idea, and we will just see few of them. A typical structure, normally a firewall is like this. This is one of the frame in a in a offshore platform. I think the offshore platforms on the superstructure have several frames, like you have one wall here, you may see some of the columns which are hidden there. So, the pink color is typically a column and the blue color is the floor beam. So, we have a firewall, safe side, unsafe side, and these kind of panels, as I mentioned yesterday, I think are designed for a specific blast pressure, and basically once the overpressure exceeds, they actually wanted to have the panel breakaway, because they do not want to create such a large pressure that they will fail the main structure, which is potentially dangerous. So, you see a situation, we want to safeguard, of course, yes, as soon as the pressure reaches that point, you do not want to destroy the structure, because structural integrity in question, because if the columns fail, what will happen? Even the temporary refuge or escape routes actually will collapse, making the whole platform to be unusable, and that is exactly the design idea, but not everyone practice this way, because this is also dangerous, because the safe side becomes very quickly unsafe as long as the temperature rise and the blast pressure increase is very quick. Suppose if it happens in a delayed period, then it is okay, otherwise you actually will be destroying the safe zone also. So, got to be little bit careful, that is where the risk will come into picture, how much risk you would like to take and how much potentially you want to have a design of these columns. Suppose you design the columns for increased pressure, then this worry is not there. So, basically that is the idea behind. So, each of these panel needs to be designed either by allowable stress method or by plastics design method. So, typically if you look at a cross section of the wall, it is just a barrier and a blast side, safe side, and you can see here the horizontal deformation. You have to design this connection in such a way that at that deformation the connection will not dislocate or the connection will not fail. So, large rotation will happen, is not it. So, basically that is exactly the idea that you need to design for. Typically for most of the fire and blast walls, sometimes people still use flat panels, just a thin plate, but as you know very well, the thin plate has got not much moment of inertia. So, if you do a moment, because it is bending perpendicular to the thickness, no. So, basically if you calculate the moment of inertia of the thin plates, it is not much, it is basically Bt square by 6, B is the width, effective width which you can consider. Whereas, if you just make a corrugation like this, simple same plate, but you bend it in this manner, you increase the moment of inertia substantially, as much as some cases 30-40%. So, you could see here when you just make the same plate bent in this fashion and this profiled plate, you will see that good increase of modulus of elasticity, and many times we use this practical applications. Typical flat plates, I have just given you a simple table which you can use it for calculation of stresses. I think if you have taken plated structures course, you will derive this. In fact, if you look at this formula, for example, you go back to this particular formula, is basically will boil down to a simple beam bending when you have the ratio of A to B. A is your length of the plate, B is your width of the plate. When the length becomes substantially larger, what will happen? Basically it becomes a beam, it is just a one way action, and when the plate is A to A equal to B, it becomes a two way action. So, whether basically is a one way slab versus those who studied civil engineering concrete design, one way versus two way load distribution. So, if you just look at the long plate, you substitute the 0.75 will ultimately will come down to your WL square by 8, something like this, basically for other A by B ratios, you have been given basic bending stress parameter, which is I think is beta, and deflection parameter, which is alpha. So, you can select, and given the loading, the blast pressure is given to you. I think when you solve a problem, the pressure is Q, this Q is your over blast pressure, and T is the thickness of the plate, and simply substitute, you will get the bending stress and you will also get the deflections. So, quite a simple and straightforward. The only reason why I gave this the table is just to make not only the beams, you also can solve plates with the boundary condition simply supported, and similarly you can go to plate fixed at all the 4 sides. You can also find the formula similar, is exactly same. When the plate length becomes longer, it becomes one way action and basically will reach 0.5. And there are 2 coefficients beta 1 and beta 2, basically the stresses at the center and stresses along the long edge. So, and the deflection coefficient is alpha, basically at the, all of them will converge to a simple beam equation once the A becomes too large. So, for solution purpose, for problem solving, the table will be given in the examination point. Suppose if this question is coming, the table will be given, but these formulas you need to remember is basically a simple m by z. If you go back here, is nothing but bending moment divided by section modulus. Section modulus is bt square by 6. So, just substitute it backwards. And sometimes we have a stiffened plate like this, basically like a floor like this, you have a stiffened the plate stiffened with several stiffness, very similar to ship construction. So, you may actually take effective flange from the floor plate for taking it as a beam action, so that you can use that in the calculation of bending stress on the stiffened section. So, empirical formula.